At this point, we've talked about how to go about interpreting experimental data to determine the order of a rate equation. And we've also looked at what a mechanism is, a series of steps that converts the reactants to products. So at this point, we want to talk a little bit about what the actual reaction involves for reactants to be converted into products. So there are a few things that must take place. I mean, obviously, the molecules must collide. But even if they collide, there are three more important factors. One is, do they have enough energy? And that's referred to as the activation energy. That depends on the temperature. The higher the temperature, obviously, the more energy that the molecules have. But in addition to those two factors, you also must have the correct orientation. So there's a typical three-dimensional orientation that the molecules have to have in order for a reaction to take place. These two slides represent a diagram that shows the energy transitions that take place in a reaction where you have two BrNOs that change into 2NO plus Br2. So what we see, and this is somewhat typical, is that we start off and the reactants have a certain amount of energy, and they reach this intermediate stage, which is referred to as an activated complex or transition state. And the energy it takes to go from wherever they are to begin with to this energy that's necessary to have a successful reaction is called the activation energy. Then after that, the reaction can either be exothermic or endothermic. In this case, the reaction is exothermic because the products end up with a lower energy than the reactants have. And over here they use delta E. And remember, we talked earlier about the difference in delta E and delta H. Delta E is the internal energy. So this would be for a reaction taking place at constant volume. And in the diagram here, what we see is just the representation of the molecules and, again, what this activated or transition state would look like before going to the products over here on the right. So as I said previously, there are several things that must take place. One is the collision. Well, one is there must be a collision. The collision must involve enough energy to produce the reaction. In other words, to get over the activation energy. So the energy of the reactants has to have at least the minimum amount of energy. The other thing is that the orientation must be correct. You are not required to make any calculations using the Arrhenius equation. However, it is useful to note that there is a relationship between the constant K and temperature. And if you make a graph of the natural log of K versus 1 over temperature, you get a straight line. So that's can be useful if you want to find out what K would be at some different temperature. But as I said, you don't really have to use that for this class. Well, I should probably have just left this problem out. In order to solve this problem, you would use the Arrhenius equation. And since you don't have to do that, then I won't go into the details of how to solve this particular problem. However, this rule of thumb is something that you should know. So the idea is that typically if you increase the temperature 10 degrees, that the rate of the reaction will double. So that's kind of a rule of thumb that we use in chemistry. The idea of activation energy leads directly to the idea of what a catalyst does. So we can understand a catalyst as something that lowers the activation energy. So if you look, this would be the reaction proceeding without a catalyst, and then this would be with the catalyst. So the catalyst lowers the activation energy and it speeds up the reaction. One important point is that it doesn't actually change delta E, so you're still going to be starting at the same place and you're going to be ending at the same place. So that part doesn't change. And we haven't talked about equilibrium yet, but I should also say that it doesn't affect the equilibrium. These two diagrams really are just another way of kind of expressing this same idea. So here we have the Boltzmann distribution. So this would be the range of energies that exist within a particular sample. And this would be the energy that most of the particles or molecules have. So typically, if the reaction is not catalyzed for this reaction, hypothetically, the number of particles that have the necessary energy is represented by the area under this curve. If we add a catalyst, what that does is it increases the number of molecules or particles that have sufficient energy. So it's kind of another way of thinking about a catalyst.